All right, continuing our look at the APC mechanics questions, version J that were released earlier today, I believe, in 2026. We've got another interesting lab design one. Just like with AP1, they decided to throw you all a curveball by limiting what you can actually measure. First off, this is an experimental design and analysis question. It is worth 10 points and the recommended time is about 20, sometimes 25 minutes. I'm going to go through some of the main things to take a look at for these. There might be multiple ways to answer some of these, but I'm just going to try and keep us moving with that. A horizontal spring of known spring constant K is attached to a wall. Block of known mass M is placed on a horizontal surface next to, but not attached to the spring. The spring is at its relaxed length when the block is at position x equals 0 as shown in figure 1. There's friction between the block and the surface only for positions x is greater than 0. As a side note, if you haven't looked at the AP Physics 1 free response for experimental design, it's actually very similar, except we're about to look at spring potential energy being lost into the work done by friction. Their question was actually gravitational potential energy being lost into friction. In fact, basically, the first part of this question is almost the second part of AP1's question, and the second part of AP1's question is almost this first part, like they've almost swapped them. So, just as a heads up, if you're preparing for future exams around the time, hopefully look for the equivalent exam and what they've released. So if you're studying for AP1, if APC happened earlier, you might take a look at it, but understand that they'd be much tougher. I really recommend that if AP1 happens before mechanics, any of you students preparing for the mechanics exam, you should absolutely work your way through AP1's released questions, because I think that would be very useful. Same thing for AP2 and APC E and M, though that might be a little bit fewer and far between, depending on what they ask. Jumping back in. Okay. Student is asked to experimentally determine the coefficient of kinetic friction, mu k, between the block and the surface using a graph. The student is permitted to use only measurements from a meter stick. So we have another very broke school district that can only afford meter sticks. Part A, indicate quantities that could be measured by the student that would allow them to determine mu k using a graph. 2, briefly describe a method to reduce experimental uncertainty for the measured quantities. Okay, I'm going to go through this real quick. The big thing that we actually need for this, and this is pretty common for part A. So first off, if you're not familiar with it, they follow a pretty solid form. Part A, 1 and 2 are going to be like they set up a thing. Part A1 is going to be tell us what we actually need to record in order to get our outcome. And they're usually using it where they're telling you, you have to generate a graph. So remember, you have to be thinking in terms of what goes on the vertical axis and what goes on the horizontal axis. The second point is to reduce experimental uncertainty, which is usually best done by doing repeat measurements. Now, please note, when you are generating a graph, you can't have this dot be one measurement and this dot be a different measurement and then claim that that reduces experimental error. If your goal is to generate a graph, doing only one measurement that would correspond to a setting, like a pullback distance, hint, hint, that's where we're going, that would not actually reduce experimental error because you're not actually doing anything that's extra stuff. You would have to do at least the number of data points in order to spread that out. Now, maybe if you said, okay, do 100 different settings to help smooth out experimental error, that might be a little bit different. But if you're only doing a couple for a graph, you really need to have a minimum of 3 dots. 4 is good, 5 is best. And that's what we'll see when we actually get to the second part of the experimental design. So whatever you're doing to reduce experimental error, I would recommend that you explicitly write, do this to reduce error. It will increase your likelihood of being able to secure that point very easily. I've read some student setups where it's not really clear why they're telling me to do something, and then I found out later that they thought that it was reducing experimental error, and it helps if you just kind of make that a little clear. Okay, so the first part of this is we're gonna have to kind of get creative. That's where most of the planning happens, and part A and B kind of go together. I got distracted a little bit. 1 point for this for the quantities that could be used, 1 point for reducing error, 1 point for indicate what quantities the student could graph. That's where you're taking the values here and telling us exactly what graph to make, and is that a reasonable graph? If it is, you get this point. If it isn't, you don't get that point. And then part 2 is briefly describe, in short, this is how do I read the graph? Usually the thing I'm looking for is going to be the slope, but who knows? Maybe you came up with a graph where it's the y-intercept. Usually it's the slope. And that's the main thing that I actually teach my students. Okay, the next thing on this is you kind of have to stop and think, depending on your familiarity with it, how am I going to work with this? Well, all I can do is measure distances. I got a spring here with no friction, but I have a known mass and a known spring constant. So these I know. Great. All I can do is measure distances. Well, that gives me a clear idea that what I would do is, okay, well, I guess I'm going to have to pull back the spring some. I'm going to bring it back over here, and I would measure my pullback distance. I would call that, I don't know, I like to call that delta x because it's a compression of the spring, but you could call it just about anything. You could call it x, you could call it d, but what I'm going to do is, okay, I'm going to pull this back, I can measure that distance, and then I'm going to let go. Well, it's going to slide forward as the spring is pushing on it, and then when it hits the rough patch over here, it's going to slide some distance until it comes to either a stop or it hits its maximum. Okay, well with that, let's see. Oh, let me check. Is it connected to the spring? Let's see. Not attached to the spring. Good, that was about to make this much more complicated because I was thinking through it in my mind. I've only half planned this out. We're going to squish this back, and this is, for my students, this is the marble launcher. This is the first lock position, and then we bring it back to the second lock position. Instead of firing it upward and putting that energy into gravitational potential energy, we're going to put this into work energy instead. So this is a work energy problem. You might be tempted to try and do something with forces, but because our big thing is we need to find the coefficient of friction. It's going to be sliding across this, so we need the coefficient of kinetic friction. There's only one equation that has that. The force of friction, kinetic friction, is equal to our coefficient of kinetic friction times our normal force. On flat level ground, we get Ff equals mu k times mg. Now my problem is I don't have any way to measure the force, but looking at the spring, if I measure how much I squish it back and I know my spring constant, that allows me to find A, the force on how much I pushed it back, but that force is going to change when I let go of it. In my class, I've reinforced to my students and anyone studying, this is a good thing to keep in mind that if you have a spring that's actually doing movement, it's not just you're squishing it and then looking at the ends of it, but if you're interested in what happens while motion is going on, you should really be thinking energy. Okay, so let's think about our energy. When I squish this back, I end up with a lot of spring potential energy. This is my notation, but the common one is U sub S. We have some non-zero spring potential energy that I put into it, and that would be equal to 1/2 K delta X squared. I know K, and I can measure delta X. That's one of the things that I can measure with just my meter stick. Then I let go of it. All of that spring potential energy goes into kinetic energy. Now, I'm not going to be able to calculate, or I'm not going to be able to measure that kinetic energy because I need to know the speed. And for that, I probably need more than just a meter stick. I might need a stopwatch along with it, or something else, or a hill of some kind to send it up with no friction. In this case, we're looking at the following. Our work is equal to our change in energy. The work, the thing that's removing our energy, is going to be the work done by friction. And our change in energy, we're going to end at 0 because it's going to slide to a stop as it goes across the rough surface. And we're going to have that subtracting off 1/2 K delta X squared, my initial energy that I put in. My 0 goes away. My work done by friction, well, it's a force applied over a displacement. So I have Ff. And here's where I'm going to put in D. The two things that I'm going to measure are how much I pull this back, delta X, I'm going to call it that, and then how far it slides until it comes to a stop, I'm going to call that D. In this case, I would have my force of friction times D times cosine of the angle between them. My block is moving this way, my force of friction is opposing that, so we would technically have cosine of 180 degrees, as we usually do, equals negative 1/2 K delta X squared. In this case, the cosine 180 gives me -1, and that just gets my negatives to cancel out. But the important thing is this. My force of friction, as we said earlier, is mu sub k mg. Multiplying that by my slide distance, d, is the work done by friction, technically negative, but now I've taken care of the negatives, equals 1/2 K delta X squared. Okay, so checking through this, I want this. And on a graph, I kind of want that to be my slope. So the stuff multiplied by it would be mgd. In this case, m, we know, that's the mass. G, we know, because that's a universe or a physics constant, physical constant. And d, we can measure. So I can actually get all of this. 1/2, that's just a number, so I know that. And then I know K, and I can measure delta X. Great, I have a plan. Here's how I can work this out. So now I can go through and do the following. My experiment, I would say, along the lines of, I'm not going to write the full thing out, but I would measure, pull spring back, and measure compression. I'm going to call this delta X. Define a variable to make it easier for your later parts that you don't have to write compression distance each time. Okay, let's see, step 2, release block, or place block on spring, then release and record slide distance to stop. The distance it goes sliding to a stop. I'm going to call this D. Now that I've defined those, I can use those. Okay, let's see, 3. Repeat 1 and 2 3 more times and average D to reduce error. You might have it where it slides a little bit more one time, a little bit less another time, but it should slide about the same distance each time, so that's why we're averaging this, because it should be about the same value. Then finally, and this is kind of an important thing that's easy to overlook, since you're generating a graph, this will probably get full credit, but as someone who thinks that this is good for you all to be very thorough on it, you would need to then repeat 1, 2, 3 for different delta X's. But we're recording the slide distance. Let's see, pull back spring and measure compression, record compression, delta X. So I'm telling you the 2 things that we need to measure, and we've got a plan to turn those into our coefficient of friction, and therefore, we've got the very first point, A1. A2, I went through, and I had repeat the first couple of steps for one given dot. These would all be on my graph. It's the same dot here. Do this 3 times, and then average those to reduce error. That's securing your second point. Now we get over to the second part of this, part B. Indicate what quantities the student could graph on the horizontal and vertical axes to create a graph that can be used to determine mu sub k. Well, we did our derivation. That's the thing about experimental design. You kind of have to do all of it together. You start with the end and work your way back, is the way that I usually describe it. We had to start off with our derivation to see how we would do this. So with this, I had the following setup. 1/2 K delta X squared. That's my spring potential energy. And it goes into mu sub K times mg times d. This was what I derived. In this case, remember, we generate a straight line by y equals mx possibly plus b. In this case, if I want to make the thing I'm looking for to be my slope, here's how I set this up. Now I can tell that I need to graph mgd on the horizontal axis and 1/2 k delta x squared on the vertical axis. That's if I want my slope to be specifically mu sub k. This isn't the only thing that I could graph. I could graph delta x squared as a function of d. So possible options are 1/2 k delta x squared versus as a function of mgd. Or we could also do delta x squared versus d, but our slope would be something different. There are other things that you could graph. You could even do delta x as a function of square root of d. What you choose to graph affects how you would interpret it. In this case, I'd recommend laying this out, maybe do some of the derivations that you see here in the space, and then say, okay, what we're seeing is our spring potential energy is going into the work done, or is being taken out by friction, by the work done by it. So if we graph our spring potential energy, 1/2 k delta x squared, as a function of mgd, the weight of the object, times, or block, times the slide distance, Then, by my analysis, we would look at the slope of that graph of the best fit line, and that would be equal to mu sub k, our coefficient of kinetic friction. You could also say we graph the compression distance squared as a function of slide distance, and then our slope would be, we could use our slope to actually find the value. It might be best for, if you're doing that, to explain that the slope would then be whatever that ends up being. I guess it would be mu sub k times mg times 2 divided by k. And so to make certain that you get the point, try and be a little descriptive on this. There are some upsides to specifically saying, hey, just graph this and this, even if it's a little bit more talking, because then you can just say your slope is equal to your answer. I would also make certain, because this will carry over to the next part as well, don't just say graph the spring potential energy. You told me that you're measuring delta x, so put your answer. You have to tell me in terms of delta x, what's going on there. In terms of d, what's going on there. You can't just say the spring potential energy and the weight or something like that. Make certain that you've got enough in here that we know exactly what you're graphing and it's in terms of what you're actually measuring. Okay. We're running low on time on this, but that's a bit deeper into how you could approach this. There might be other ways to do a lab design on this, like the graph. You could do several different things, but I don't know that there's a solid way that you could get full credit on the other. Maybe I'm just not thinking about it. Okay, on this one's going to go a little bit quicker, luckily, because I came prepared. In a different experiment, they basically set up, we got a new spring. We don't know the spring constant, but we do know the mass of the block. And this time we're going to squish it up. We're going to launch this thing up, and it'll slide up a ramp that I believe has negligible friction. Yes, negligible friction. Our goal is to analyze this problem. It goes up to a maximum vertical height, h, as measured from, I believe, the center of mass. I'm certain that's what they're actually implying here. That's what the drawing actually shows for the center of mass. So in this case, we have spring potential energy that is going into gravitational potential energy. Once again, for my students, you did something very similar to this with our marble launchers way back when we were doing Unit 3. Okay, we have a table of data. In this case, I'm going to show you real quick. Now that I know that I'm taking spring potential energy, US, and putting it into gravitational potential energy, UG, I can do 1/2 K delta x squared, or in this case, they're actually calling it S squared, equals mgh. We want this. But we need to fill in the other things. We know this is 2, we know this is 10, and we have data for H and S. Great, this gives me a clue as to what I can do. Writing this out, I'm going to rework this a little bit. I could do mgh, equals K times 1/2 S squared. I could do this. Graph this on the X, graph this on the Y, and then my slope would straight up be my spring constant. While that would be nice, one of the things that I'll point out is this is a lot of math that you're going to have to do on each of the individual bits of, like you're going to have to do this with every single one of them. A lot of times the safest thing to do is to try and get this as simplified as you can in terms of what you're working with. So here's what I'm going to do. I'm going to move this around just a little bit more, and I'm going to have H equals K over 2mg. 2mg, great, and then S squared. I'm given S, so all I have to do is take those numbers and square them, and I'm given H, I don't have to do any math on those at all. This is usually one of the safer ways, at least with time constraints, to actually do that. If you do one of these others, it's great, it works out just fine. The problem is you're going to then have to take all of your H's and multiply them by 20. That's a bunch of typing into your calculator. You're going to have to square this and then divide it by 2. Whereas with this, you take H exactly as it is, no math required, and then S, square it, you're going to have to do a little bit, but then you graph this. I'm going to recoup some time and do something that you all can't do. Oops, forgot to move it over here. I cheated. I didn't actually, because you can do this in your calculator. If you do this, make certain that you write linear regression. That being said, I'm going to save us the time of me manually graphing this. We can see here, it's not quite 6 units, so this isn't necessarily the best ever, but you can see I've got it properly marked. Here are things that you do need. You need to mark your vertical axis with units. You need to mark your horizontal axis with units. What I've graphed here is H as a function of S squared. So I went ahead and graphed that. I took, here's my raw data, I squared that, and then I had Excel generate the graph for me. You do need to be able to graph this by hand. We put the dots in, I get out my clear ruler, I do my best fit line to the best of my abilities, and I find that my slope is 31.95. So my slope on this graph is coming up to be, when I graph this one, my slope is coming up to be, from my analysis, 32 with appropriate units. In this case, I believe it is 1/meters, because this is in meters and this is meters squared. But that being said, honestly, as long as you put SI in, you'll get SI out, though I suspect I may not have this fully in SI. Okay, that being said, I mean, it is in SI, but these seem like really, really low numbers. So 32 is my slope, and that will be equal to, according to my analysis, K/2mg. I'm going to pause here for just a moment. Let's double check that we know where your points are coming from on this. Part C, label the axes of the grid provided with measured or calculated quantities. Now remember, if you're calculating your quantities, you need to express where they're coming from in terms of the measured quantities. Don't just say, okay, we're going to graph gravitational potential energy and not tell me that you're doing the mass times the acceleration due to gravity times h. Always put mgh. Use the things that you've got the data on. I have a bunch of students that give me stuff that they put it through an equation, I don't know what that equation is, and they just call it the acceleration, and I'm like, I have no idea where this is coming from. I don't even know where your number's coming from, for that matter. Always put things in terms of the values that you're given. If you're given h and s, you should have h and s somewhere in these when you're working with it. Okay, so we mark these, and units. You must do both to get that first point. And this point also kind of relates to linearizing as well. If you don't have something that you can linear, or if your graph isn't linear, you may not get this first point. If you do not know what to graph, if you don't know how to go through and do the derivation, a safe thing to do, if you don't have anything better, graph the data you are given. Please, please, please do that, because there are plenty of points, as we're about to see, for graphing correctly. For this graph, for APC mechanics, I'm pretty certain you have 2 points that are related to the graph itself. One of them is for having a uniformly spaced axis. So don't go like 1, 2, 17, 352, 7,922. Have it evenly broken up, 10, 20, 30, 40, 50, 60, right? That's one thing that we're looking for. For APC, make certain that you are spreading your graph out on at least half of the axes both ways. If you squish your graph into the corner here, I don't know if they're still doing it, but I expect they are, then that is one of the points, that's one of the things that we're looking for. You need to spread this out enough. It doesn't show up as much on the AP1 exam, but the AP1 exam, they usually fill in one axis now and do a bunch of the work for students on AP1. Again, APC is just mathematically much more rigorous. Okay, so the 2 points on there, one of them is for good graph design, having these linear, like properly spaced out and things marked appropriately, and that your dots are spread out so that they're not squished into the corner. The second point for good graphing is whatever you tell us where you're going to graph, or the dots that are provided, you get those dots in the correct spot. It used to be on older versions of the APC exam many years ago that I think it was like as long as you had 4 out of 5 of them in the correct spot, then you would get the point. All the grading rubrics that I've seen thus far, I may update this later after I go to the reading and see what it's like with the new setup, but they haven't given a lot of wiggle room. They just say get the dots in the right spot. So take the extra minute to make certain that you get the dots in the right spot. And when you are spacing things, you are not required to go to the outside edge. You just need to use at least half of each axis. Use something where you have this in like 10s or 5s or something like that. I've had students where they try and break it up so that they fit this perfectly, and then these are going like 0.8 is here and then 1.6 is here, but then their dots end up off because it's not an easy scale to read. Do yourself and the grader a favor by trying to come up with something where don't go the entire axis, you don't need to do that, just need to use more than half of it, and put the dots where they actually go. So those are the 2 points for the graph. Scale and spreading it out, and then the other is dots in the right spot. There is the next point on the graph, which is using your ruler to do a best fit line. Please, please, please use your ruler. For my students, I send along clear rulers to the AP exam when you take it, and use that to actually draw your best fit. Okay, next up, part D, using the best fit line you drew, calculate the experimental value. For me, again, I'm cheating a little bit, although not necessarily. You can always do a linear regression off of the data. If you do that, please include in your solution that you are using a linear regression. That was something that we had in the old APC. I don't know if it carries over to the new one, but it's still a good habit to get into. If you have a number that appears to come out of nowhere, tell the grader where it's coming from, just so we have an idea of what you're doing. In this case, we have about 32. 32 is therefore equal to k over 2mg. The first point in this section is for you correctly matching basically this, taking the thing on your graph and correctly relating it to the thing that you're looking for. So when I see that my slope is 32 and that you know that it's equal to k divided by 2mg, then you're able to get that point because you're connecting those two things. If you take the extra time to do a graph that you're graphing a vertical and a horizontal such that the slope of your line is the thing you're looking for, I think you basically get that point pretty much for free as long as you're solving for your slope because you've done the extra step of making that slope the thing you're looking for. But otherwise, take the extra time and show us this so we know what you're thinking. 32 is therefore equal to k divided by 2. The mass of this thing was 2, and the acceleration due to gravity is 10. So we would end up with, let's see, 32 is equal to k divided by 40. Oh, I was doing this wrong in my head. So I multiply both sides by 40, and we would end up with about 1,232 times 40 gives us about just shy of 1,300. So k new would apparently be equal to about 1,280. Since I put SI in, I should get SI out, Newton per meter. And that's actually, it's a decently stiff spring, but that's within the range that I would expect. For some reason, I was thinking it was around 1. I was doing it wrong in my head. Anyway, I think this is about what you would get, at least me graphing it and doing the linear regression here. I haven't done it by hand to save us some time. All right, I think that's pretty much everything I've got for the experimental design. Until next time.